So anyway, so welcome everyone, and we're very happy to have Ting Zhou from Zhejiang University. And so Ting actually joined the year before I graduated. So she was also a student of Gunther Ullmann, and so she is going to talk on inverse problems for Maxwell's equations. So over to you, Ting.
Okay. Thank you, Venki, for the invitation, and I really enjoyed the opportunity to give this mini course on inverse problems for Maxwell's equations. Please feel free to stop me anytime to ask questions. So to be more specific, these are inverse boundary value problems for Maxwell's equations. To put in context, you can think of them as natural generalization of the Calderon problem for the conductivity equations, where Venki was talking about. So my talk will consist of mainly two parts. First, I talk about the inverse problem for linear Maxwell equations. Then I talk about the inverse problem for Maxwell's equations with nonlinearity. This would be modeling some nonlinear optics. So we're focusing on recover some nonlinear second harmonic generation or Kerr-type nonlinearity for the medium, this kind of electromagnetic properties. So if time permits, I will be digress a little bit, talking about some inverse problem for magnetic Schrodinger equation, where we use the partial data. That means the measurements are taken only on part of the boundary. So we can see some typical macrolocal analysis we used to prove some kind of a density of product of solutions in certain function spaces. So because in the second part of the nonlinear equations case, this is a theme. Essentially, you want to show certain density of a product of solutions. So I feel it is not too much digress from the topic by mentioning this third part, but only time permits. Right? Okay, so we'll focus on inverse problem for linear Maxwell's equations now. So this is, as I mentioned, essentially looking at inverse boundary value problems. We are hoping to uniquely recover some electromagnetic properties of an object. Other than only conductivity, we want to also try to recover permeability and the permittivity. So it's a full set of electromagnetic parameters. The measurements we're taking here are also boundary measurements. Essentially, these are measurements of electromagnetic waves. And in particular, we see time harmonic solutions for the Maxwell's equations. And we'll see in order to get this information, we only need to measure the sort of tangential component of E and H, this electromagnetic fields. So E is for electric fields and H for magnetic fields. So the new here is the outer unit normal to the boundary. So here in this picture, the boundary is kind of smooth. So in our analysis my work partly with Pedro Caro, are dealing with less smooth parameters. So there are previous results for, let's say, C2 parameters, mu, epsilon, and gamma, and also for smooth boundaries. But in our work, we try to relax these conditions by assuming, say, C1 parameters, and also the boundary being Lipschitz. So that is also a focus of this talk. Okay. So that essentially answering the two questions: can we uniquely recover these parameters? In short, yes. And what kind of these parameters can be recovered? We consider C1 parameters and also the boundary being less smooth, like Lipschitz. Okay. All right, so let me first talk about the time harmonic Maxwell's equations. We consider the most general time-dependent Maxwell's equation given here in a bounded domain omega with Lipschitz boundary. And we assume linear constitutive relations. So this is the linear medium, where B is related to H by the permeability. D is related to E by epsilon, the permittivity. So the current J will be conductivity multiplying the electric field. Okay. So mu, epsilon, gamma, these are the three parameters for our that we are interested in reconstructing. Okay. So time harmonic solutions for these time-dependent equations are taking this kind of ansatz. You have this separation of variables. So e to the I omega t, omega will be the angular frequency. So plugging this back into the Maxwell's equation and only consider those equations for E and H depending on the X variable, then we'll get this time harmonic Maxwell's equations. Okay, kind of symmetric for E and H. And here it will be mu, but here will be a complex coefficient with real part being epsilon, the imaginary part giving you the conductivity gamma x. Okay, so this is for a fixed frequency time harmonic Maxwell's equations. Okay, here on the left in this box, we have some basic assumptions on the mu, epsilon, and gamma. At this point, we assume them to be L infinity and asymptotic to be some constant outside the domain, or can be theoretically extended this way. So, and on the right will be our boundary measurements. You can think of this as analog to directly to Norman map in the Calderon problem. But for Maxwell's equation in electromagnetism, this is so-called admittance map, which, as I mentioned, is you can think of the measurements of the tangential electric field with corresponding tangential magnetic field. So the E and H are the solutions to this time harmonic Maxwell's equations. Okay. So our inverse problem here is naturally, can we recover mu, epsilon, gamma altogether from the boundary admittance map? Keep in mind, I'll be introducing results for Lipschitz boundary and C1 parameters. So I think I'm missing some letters in these slides, but this is just to recall as a comparison, parallel comparison of the Maxwell's equation case and the Calderon problem, where you only focus on recover the conductivity, where for the electrical impedance tomography, these are sort of motivation of this Calderon problem. Is can we recover the conductivity or determine uniquely the conductivity from the boundary physically voltage to current flux map, mathematically the directly to Norman map. So again, for the Calderon problem, we look at the equation to be this elliptic equation, but for electromagnetism, we look at the Maxwell's equation. So usually people consider this case being electrostatic corresponding to, say, zero frequency limit. That means in the Maxwell's equations, you take frequency omega going to zero. The Maxwell's equation could be approximated by this conductivity equation. So for Calderon problem, you use a direct to Norman map, which is the voltage to current flux at the boundary. And for the Calderon problem, we ask, can we determine the conductivity uniquely? Or how can we reconstruct the conductivity? Or how stable this process is? Here is our main result with Pedro Caro on inverse problem for Maxwell's equations. As I mentioned earlier, we assume the boundary to be Lipschitz and the parameters belong to C1 space. And for a fixed frequency, if you have identical boundary admittance map for the two sets of parameters, we can show first the boundary uniqueness. That means we can recover the parameters and up to their first derivatives, since we assume them to be C1 on the closure of the boundary domain, to be identical on the boundary. So this is known as a boundary uniqueness or boundary determination of the parameters. So this is actually a required step or a pre-step to show the second part, interior uniqueness of the parameters. So this will be the second part of our result. All right, so I'll be talking about the boundary reconstruction first. So let me again put everything into the context, talking a little bit about the previous results of the boundary reconstruction for the Calderon problem. The two papers mentioned here, Cohen and Vegelius in 1984 and Sylvester and Woman in 1988, this is essentially all set up in smooth conductivity and also boundary being smooth. So they were able to uniquely recover the boundary value of the conductivity. And moreover, in this 88 paper, they show that DM map is a pseudo-differential operator whose symbol expression can give you the conductivity function and its first derivative, or higher derivatives, depending on which term you are looking at in the expansion. But both are set up in the very ideal situation, like when you have the boundary being smooth and conductivity being smooth. So in this paper by Brown in 2001, this was generalized to Lipschitz domain. The domain was Lipschitz boundary. Essentially, it's following the idea in this pseudo-differential operator to prove this simple expansion. But the way they do this is to test the DM map against the highly oscillating solutions. Okay. So as a parallel discussion for Maxwell's equations, down to the second paper here for Maxwell's equation was done by Somersello in 1994, where he showed the symbols of the admittance map and the map, inverse map, the impedance map for smooth boundary and smooth parameters.
Can I ask you a question?
Yes, of course. Go ahead.
So in Brown paper also, that for the Lipschitz, he assumes it is C infinity conductivity.
No, here you can assume it to be C1.
I see.
It can be any kind of regularity, I think. If it's just continuous, you can just, I think you can just recover the value of the parameters. Yes.
So if I understand it correctly, so he generalizes in both ways. That is, he assumes less regularity on the conductivity and also less regularity on the domain, on the boundary.
Right. But I think the difficulty part is really the boundary being Lipschitz.
I see. Okay.
Mm-hmm. All right. So as I mentioned, the idea of the proof is testing against highly oscillating decaying functions. Here is a little bit technical, but let me try to explain. So we are interested in recover the value of conductivity at a point on the boundary. So what we do is we first do change of coordinates, try to flatten the boundary and set that point being the origin. Then we choose the EN being the normal direction to this part of the boundary. So you have a nice coordinate system. In that coordinate system, so say X being X prime, XN. So XN would be the coordinate corresponding to EN. And this would be the function, a family of function depending on this large parameter N. So eta here is a cutoff function. So you have this support kind of for the X prime and XN using the N parameter. And also you have the oscillation by this last part, exponential. So the alpha here being a perpendicular direction to En. So when we have this kind of oscillating decaying function, and the key lemma here, of course, this comes from the pseudo-differential operator, how you extract the symbol. The first term of the expansion is to show that the gradient of these functions, the energy essentially associated to these functions for the conductivity equation actually has this kind of asymptotic order with respect to n. Okay, so this way you can extract the value of gamma at 0. Essentially is the value of the conductivity at the point we're interested in after before we do the change of coordinates. So this is the key lemma we focus on. So back to our Calderon problem, recover the boundary values. You apply the DN map to this function restricted on the boundary voltage on boundary. So the UN will be the solution to the connective equation, but matching this VN on the boundary. And it's not hard to get this identity first, the blue identity part. And this energy can be split into two parts, roughly speaking. One is the term that we wanted to use in the lemma, okay, so that we can recover gamma of 0. And then you have the remaining part. The second term here can be controlled or absorbed by the first part, or considered to be small by elliptic regularity. Just consider the equation satisfied by this difference, and you are able to show this little o of with respect to the half of 3 minus n power of n, which again, comparing to this leading order term here, is a small term inside here. Okay, and that was essentially hard to deal with because of Lipschitz boundary, where he used the hardest inequality. So that was Brown's work for the Calderon problem, but for Maxwell's equation, we do similar things. You do this energy identity. Essentially, you set the boundary tangential fields for the tangential electric fields to be the gradient Vn, the tangential component of the gradient Vn on the boundary. The idea was inspired by you want E. So in order to recover, say, this complex coefficient sigma, whose real part to be epsilon and the imaginary part give you the gamma, then you want E essentially to be the gradient Vn. So you can apply the previous lemma, right? That was the hope. Then you can do the same for the second term. What you do is you set the boundary to be the tangential component of the gradient Vn, and to show that E is roughly the gradient Vn. Okay. Again, using this identity, you can split this energy term into 3 parts. The main part, you can apply the lemma, and the remaining part shown to be small using similar kind of irregularity result for Maxwell's equations. And here things are different because of the spaces that we used for the Maxwell's equation, that you need the L2 dual space of the H curve space. That is a natural space for the solution for Maxwell's equations. So there are some technical details in this proof that you need to handle and using the structure of Maxwell's equations. So it's not completely a trivial extension of the previous results. Okay, but here is just to show you a general idea of the case for Maxwell's equation.
So I think can you just recall what the Vn is? Vn is from the previous slide.
Sorry, Vn will be here.
Okay, all right. I see. Okay, all right. Yeah, thanks.
So yeah, so this would be for the Maxwell's case. And similarly, you can adjust the boundary values so that you can recover the mu by setting H being the roughly gradient Vn. Okay, so that can be achieved. Of course, this only gives you the value of the parameters on the boundary. In order to recover their derivatives, the gradient sigma and the gradient mu, we use a different integral identity. Also can be obtained by manipulating the values of electric fields and magnetic fields on the boundary. So it's a little bit complicated, this formula. However, you can see on the boundary, on the right-hand side of this equation, we use some normal component of electric field and normal component of magnetic field. And the alpha, which is perpendicular to nu, can be also obtained using similar idea. Like alpha is a arbitrary direction perpendicular to nu. Okay, so the normal condition here, because for the admittance map, we only have the tangential component. But using the Maxwell's equation, we can get a normal component of electric field by taking the surface divergence of the tangential magnetic field. So this again borrows the feature from the Maxwell's equations. And that way we can really compute this complicated right-hand side of this equation in order to get the left-hand side, where you have the same structure as before, and you set E1 and E2 being the gradient Vn. Sorry, the F here, let me mention here, F will be the tangential of the gradient Vn. So it's a little bit technical, but you should be able to recover alpha dot gradient sigma and alpha dot gradient mu. So this completes the boundary reconstruction of the parameters. Okay. So now I show you the ideas for interior uniqueness proof of the parameters.
Sorry to interrupt, just one question. So then I think the higher order derivatives using this approach will be complicated, like the integral identity that one would get for as the derivatives get higher and higher would be more complicated.
Right.
Okay.
But I think if you assume, so yeah, I assume that this integral identity have the version for higher derivatives. The only thing you need to use probably is just a normal component of the curl of the electric field and the magnetic field.
I see. But are there, like, I suppose there should be pseudo differential operator methods, and then
right.
doing
that would be sufficient.
Okay, I see.
But you don't really need to. Yeah.
But on the other hand, my only thing is, like, if you have only finite regularity, right? Then pseudo differential operators methods are
right.
I don't know.
With the Lipschitz boundary, that was an issue. Yeah.
But I suppose for the inverse problem, you only need you only need information about the conductivity or all these parameters and its first derivatives. That is enough, I suppose.
Yeah, that was for C1 parameters in our results. Yeah. And for the interior uniqueness, yes, the boundary uniqueness of the first derivative is enough.
Yeah. Okay. Thanks.
Okay. So for the interior uniqueness, let me also go back to the Calderon problem to remind you of the CGO solutions, because that's essentially what we are going to construct for Maxwell's equations as well, and to show the interior uniqueness. Also, because we are considering less smooth parameters here, and I want to show how, just to summarize how the same analysis was done for the Calderon problem, and how we can translate that into the case for Maxwell's equations. So if you recall, for the conductive equation, you basically can construct, first reduce that to a Schrodinger equation, minus Laplacian plus Q, where Q here has the derivatives of the conductivity function, gamma. And the way you do this is to construct the so-called CGO solutions by first looking at a harmonic function e to the x dot zeta, the complex linear phase exponential. So the zeta here is a complex vector satisfying zeta dot zeta equal to 0. You have the product of two CGO solutions with two complex vectors being conjugate of each other, then you should get the free exponential e to the 2I could c. So if you have all directions could c, then you really multiplying by this of the conductive or of the potential Q, you get the Fourier transform, right? But since we have the potential Q, we are looking for the solution for the Schrodinger equation, and this was taken care of using this kind of perturbation idea by introducing this tail psi to have this kind of smallness going to 0 with respect to the magnitude of this complex vector zeta. So that was the CGO solution. And the idea is that you plug in this CGO solution into the integral identity for the Calderon problem and letting magnitude of zeta going to infinity, and eventually you will the integral identity will convert to the Fourier transform of the potential Q. So once you recover Q, you can recover sigma, the conductivity. So that was the idea. Here I want to also give a slide of summarizing the construction of the CGO solution, more precisely the proof of constructing this tail by using sort of functional analysis steps. Then we'll show later and see how this could be relaxed a little bit to incorporate like less smooth parameters, right? So if you recall that you conjugate the Laplacian with this complex exponentials, then you get this particular operator Laplacian plus 2 zeta dot gradient, okay, for the psi, which is the tail in the CGO solution. So here will be the equation you obtain for the psi. And formally, if we assume this operator Laplacian plus 2 zeta dot gradient to be invertible, okay, then this box equation will be what you are looking at. So yeah, this is the first thing that I will assume this being invertible from y to x. So the inverse will be from x to y space. And MQ here is just multiplying by the potential Q, okay? So that will be an operator from y space to x. Then the composition of these two together will be from y to y, okay? And looking at this equation, the functional analysis tells you that if you can show this term here, this operator, the composition of these two operators being small, as the size of magnitude of zeta going to infinity, then the whole thing will be invertible. The red part, the operator will be invertible. So you can really solve for psi using, say, Norman series kind of construction. And in particular, we want psi being small, and this should be given by the smallness of the right-hand side of this equation, which in most analysis we're seeing will be coming from, again, the smallness of this operator. Okay. All right, so keep this in mind. We look at different results, improving the previous results in Silvestri and Women's paper, where they consider gamma being C2. Okay, the conductivity, when it's C2, the potential Q is taking this format, the Laplacian of the gamma square of gamma over square root of gamma. So that would be a L infinity function, and it is a complex supported. So the idea there is to show the smallness of this conjugate operator, inverse conjugate operator, from X to Y in this L2 weighted space. Okay, this is what they have shown there. In a later paper, this was generalized to less smooth conductivity, assuming 3/2 plus a little bit more than 3/2 smoothness for the conductivity. And you can imagine with this gamma, the Q here should be of negative regularity. Okay. And the idea here is to show an estimate in a weighted Bessel space. So if S is between 0 and 1/2, you can still keep this decaying property with respect to the larger of the magnitude of theta. At the same time, you can show MQ, the multiplication by the potential Q is a bounded operator. Okay. Here, assuming that gamma 1/2, the first derivative in this Bessel space being bounded. So this was done using the weighted Bessel space to show the uniqueness of the conductivity with less than C2 regularity. But there's a limitation of this method, partly because they were only able to show this decaying property when S is bigger than 1/2, and this is no longer decaying. So, and the recent, not so much so recent, I guess it's been a while, but a breakthrough was done by Haberman Tataru to show the Calderon problem, to prove the Calderon problem for C1 conductivity, or the gradient logarithm of gamma being small. So what they did was to introduce this Born type space, where you actually, P zeta could see here is the symbol of this special conjugate operator. Okay, so what they did here is incorporate this symbol into the space. Naturally, the inverse of the conjugate operator in this Born type space has the operator norm being 1. However, they were able to show the multiplication by potential Q. Let's go back here in this equation here. Keep in mind that we want to show this whole thing, the composition of these two operators being small. But in previous work was showing this being small and the second MQ being bounded. But here they did it invertibly, saying that MQ being small, but this inverse operator being bounded. Okay. And also the smallness of the remainder psi was also requiring that the Q being small in certain sense. And they were able to show this in an average sense, like the very lucent sense with respect to the large of magnitude of theta. So I guess I should mention that the analysis here relies heavily on the compact supportness of the potential Q. So they were able to show this average sense decaying property. All right. So for the Maxwell's equation case, okay, interior uniqueness for the inverse problem for Maxwell's equation. Let me first mention the previous result for the problem. It's basically a parallel development as the case for Calderon problem. Like for the Calderon problem, Calderon introduced the linearized problem, solved the linearized problem, and Somersello and Isaacson and Cheney in 1992 they solved the linearized problem, and later for the nonlinear inverse problem. But for the linear equation, Ola, Pivarenta, and Somersello they solved the inverse problem for smooth parameters. It says C infinity, or maybe can be improved to C2. And this third paper by Ola and Somersello in 1996 This is more close to the scheme of the proof in the 87 paper by Sylvester and Woman, where you have this natural reduction from the conductive equation to the Schrodinger equation. Here is you can think of as reducing the Maxwell's equation to the Schrodinger equation. For Maxwell's equation, there's a little bit tricky thing here is because Maxwell's equations are not elliptic equations. So you have to first reduce that to a first order Dirac system, which is elliptic. And I'll talk about that a little bit more in a bit. Okay, but just to mention that, but as a result, Olar-Marcello's paper actually is only simplifying the second paper here, not giving too much new like improvement of the results for the parameters, still working for C2 and higher regularity coefficient parameters. But the meaning of this work is that this reduction to the Schrodinger equation technique was carried over to later works when dealing with inverse form for Maxwell's equations. Okay, yeah, here is the summary of their reduction to the Schrodinger equation. How you do this for Maxwell's equation. For a Calderon problem for conductive equation, it's kind of easy. You just apply a so-called Delaware type of rescaling. But here we first deal with the non-ellipticity of the Maxwell's equation. As we know, we can take the divergence of the two Maxwell's equations and we get this divergence-free equations, and we put these together. We have 4 equations for E and H. And then we introduce this so-called Sommerfeld potentials, but this essentially scalar potentials taking the format of divergence of epsilon E and divergence of mu H. Okay, so if you introduce these 2 scalar potentials as new unknown variables for the set for the equations, so you basically have a 8 vector variable with the 2 scalar potentials phi and psi, and at the same time adding the magnetic vector and the electric field vector. So it's an 8 vector. You have 3, 3 plus 1, 1. So it's 8 component in this vector. So you have a system of 8 vector. And this system, after a Delaware type rescaling, similar to the one you did for the conductive equation, there's a lot of verification for the computation here, which I'm skipping. You will get this P minus K plus W X. X will be this variable equal to 0. So this becomes an elliptic first order system. This is like 8 by 8 matrix, this red part. The K here is the wave number, okay? So here is more statement on the P operator. The D will be the imaginary gradient. Then this is the D dot, and this is like a curve. Okay, so you can check that this is indeed the 8 by 8 differential operator. K will be the wave number, and W will have the coefficient, the parameters, and the first order derivatives of the parameters. The idea here is that this P plus K minus WT as a square root, like roughly speaking, a square root of the Schrodinger operator, kind of matrix Schrodinger operator, of course, with the non-zero wave number. So before, for the conductive equation, you don't have a K. K will be 0. You have minus Laplacian plus potential Q. But here you have a non-zero wave number, and also potential Q will be WWT. So that will be involving the second derivative of the involving the parameters up to the second derivative, okay, of mu and epsilon, and also gamma, the conductivity. Okay. So what do we do here? Keep in mind that our original Maxwell's equation is reduced to this elliptic first order Dirac system, T minus K plus Wx equal to 0. And if we write the ansatz for X being the other half of the Schrodinger operator, applying to a Y vector, also 8 vector, okay, then this new Y will satisfy the Schrodinger equation. Okay. So what we're going to do is to construct the CGO solution for this Schrodinger equation for Y. So that is like the same as what we did for the scalar case. And applying the second half of the operator to Y in order to get X, which is the solution for this first order elliptic system. Okay, and then we're gradually going back, so we get a solution for E and H, because the second component gives you H, a second component of X gives you H, and the last component of X giving you E. With a little bit catch here, is that in order for X giving you the second and last component giving you the solution for the original Maxwell's equations, and you can easily see that the scalar potentials phi and psi, which are the divergence, have to be 0. Okay, so not every solution for this first order elliptic system gives you the solution for Maxwell's equation. Only those ones with 0 first component and 0 third component give you the solution for Maxwell's equation. So that's the only thing that you need to check every time you are looking for solutions for Maxwell's equations using this type of reduction. Okay, so that's what I wrote down here for X being the solution of this first order system, and then the first and third component being 0, then you can have the second and fourth component being the solution to Maxwell's equations. Okay. So the next will be how to prove the main steps to prove the interior uniqueness for C1 parameters for Maxwell's equations. It's similar, it's completely parallel to the case for the Calderon problem. But keep in mind, we are looking for the proof for C1 parameters. So it's more similar to the one in Haberman and Tataru's paper, as I talked here, for gamma being C1. Okay, that means we also adopt this Bergen type space for our analysis. Okay, but before doing that, we also need to derive an integral formula as similar to the proof of uniqueness in Calderon problem from identical boundary measurements, in this case, admittance map, able to show MQ2 minus MQ1. This is multiplication by the Q2 and multiplication by Q1. Applying to the Y1, and keep in mind Y being the solution for the Schrodinger equations associated to Q1. There's a slight requirement here for Y1, that is the X1 has to give you the solution to Maxwell's equation. So that means the phi1 and psi1 being 0. But for X2, we don't have any kind of restriction. As long as it's a solution to this first order elliptic system, even if it's not a solution to Maxwell's equation, it's fine. Okay, so that's kind of anti-intuition here, but it is the proof shows that you don't need to put any restriction on X2. So the only thing we need to really check, especially when we adopt this Bergen type space in our proof, it is hard to check that the X1 does give you the solution to Maxwell's equation, because you need a uniqueness for the equation, for the solution of the equation in order to show this, which usually is the hardest part to do this kind of analysis for Maxwell's equations. I just want to point that out. I guess I still owe you this a little bit technical part for constructing of CGO solution for Maxwell's equation. As I mentioned, you construct CGO solutions for the Schrodinger operator, that is Y, taking this format. That A here, I call it amplitude, but it's really playing the role as 1 in the CGO solution for the conductive equation in Calderon problem. Okay, so the precise theta is small in the Bergen type space in an average sense. So these will be the steps to guarantee eventually you get x1 and x2 as required in this integral identity. So you have to carefully choosing the amplitude for y1 in order to guarantee x1 give you the solution to Maxwell's equations. Okay, but we don't have such restriction on x2. Only need the smallness of the remainder part. And this was done for x2 essentially by noticing that if we apply the other half on the left-hand side of the equation, then we also get a Schrodinger equation, but with a slightly different potential Q2. So I denote that Q2 tilde here for x2. Then you can construct CGO solution here. And this is safe because, again, we don't require x2 to give the solution to Maxwell's equations. So. And everything is fine, and you can plug in the y1 and x2 to this integral identity here. As a result, you should get a sort of Fourier transform of q2 minus q1. And also should multiply in the amplitude a zeta 1, a zeta 2. And the first item here is just to show that the remainder part being small. Okay. So the right-hand side of the integral identity after plugging y1 and x2 convert to the Fourier transform of the first and last diagonal component of q2 minus q1. Keep in mind q2 and q1, they are similar to the q2 and q1 in the scalar case, which essentially is the Laplacian of the parameters over the square root of the parameters. Very similar format. So the diagonal component, the first and last component, will give you the final proof saying that the two sets of the coefficient being identical to each other. But it's not so trivial here. You need to develop a unique continuation property for this system here. But this is again a little bit technical part. So I'm not going to elaborate too much. Okay, so that completes the proof of interior uniqueness. So essentially, they are similar to the proof for Calderon problems, but a little bit technical here and there. And especially when we are dealing with Lipschitz boundary and the C1 parameters. So this concludes the first part for inverse bound for linear Maxwell's equations. I guess I still have 10 minutes for the first hour. Let me go ahead and start the introduction for the nonlinear Maxwell's equation case.
So Ting, can I ask a question?
Yes.
So what about for the partial data results where for the admittance?
Right, for the partial data, yeah, I didn't mention anything here, but for Maxwell's equation case, yeah, the results are completely different from the Calderon problem, as you know. So Calderon problem, the partial data that you have the tool of the Kalman estimate. So I'm sure Venki has talked about using Kalman estimate to construct CGO solutions vanishing on part of the boundary. So there are many works done in this direction. For Maxwell's equations, the Kalman estimate approach requires very restricted geometric assumptions on the parameters, I guess. So there are basically two approaches. One is actually using the Kalman estimate. The other is using this Issakov's reflection method by using the Kevin transform. So you can introduce this transformation, which is essentially reflecting with respect to a plane or with respect to a sphere. Okay, and then by adding these two solutions, then you can prove that you can get a solution that vanishing on that part, the flattened or a spherical boundary. And using that kind of CDO solution, that you can prove certain partial data result for Maxwell's equations. And that's one approach. And the other one is more, I guess, using the Calderon estimate for anisotropic Maxwell's equations, where you assume this kind of cylindrical coordinate metric for the manifold, and there you can develop certain kind of Calderon estimate. But I'm not too familiar with the approach, but I think the traditional Euclidean case using the Calderon estimate, why it doesn't work for Maxwell's equation is essentially what I have shown here is this last step here to check that the solution X, although you have a CDO solution there, to indeed give you the solution to Maxwell's equation, requires you to prove this middle part, the scalar potentials being 0. And there requires a uniqueness of the solution where you've done that using the Calderon estimate. I think using Calderon estimate, the only thing you are missing is the uniqueness of the solution for the equation. So that's what's missing, and why it cannot be generalized to the Maxwell's case. I hope that answers your question. Okay.
Yeah. Okay. Yeah. Thanks.
All right. Okay. For the nonlinear Maxwell's equation, I guess I'm skipping this slide, which is essentially repeating the Calderon problem. And this is what I talked about for the linear Maxwell time harmonic Maxwell's equations, where we were able to recover the parameters. This I put it here essentially to give you the roadmap of how to prove the Calderon problem, where you first reduce to the Schrodinger equation and ask if we can determine the potential Q from the boundary DM map. And the key step here is to develop this key integral identity. This is important. I wanted to put it here because later you will see for the nonlinear equation inverse problems, we do higher order linearization. And as a result, we get very similar integral identities. The only thing different is that instead of a product of 2 solutions, we actually get a product of 3 or more solutions, depending on the order of the nonlinearity in the equation. Okay, so that is apparently the basics for solving this inverse problem for nonlinear equations by doing higher order linearization. Okay, then question becomes, this is for CDO solution. Essentially, what we did for Calderon problem is to ask, can we have enough solutions so that the product of the 2 solutions is dense in the function space, so we can really get a Q1 minus Q2. So this was shown using essentially U1, U2 being CDO solutions. We really get a free transform of Q1 minus Q2 for all the free variable could see all the directions. And this was down here. So the sum of the 2 complex vectors give you I could see, and for many could see directions. So this also asks for a degree of freedom of could see. Okay. Yeah, that's why I want to show you this again, although you have seen such things in last few days. But especially I want to point out that integral identity like this will be very similar to the ones in the inverse problem for nonlinear equations. Okay. Yes. So let me just show you by the idea of this linearization approach by talking about inverse problem for nonlinear conductivity equations. Okay. And so for nonlinear conductivity equation, so you can think of a Calderon problem for nonlinear conductivity equations, I guess. where you assume the conductivity. Here I call it sigma before I call it gamma. So please, I apologize for the misuse of the notation. But sigma here, now we assume it depends on not only the x variable, but also the solution and the gradient of the solution altogether. Okay, so that's where you introduce the nonlinearity. So you can show under a certain assumption, this equation is well posed when your boundary directly condition being small enough. Okay? And in that regime, you can show the well-postedness or well-defined DM map, directly to normal map, from the boundary value of U to the, again, the normal boundary condition. So the inverse problem is to ask, can we determine sigma from this DM map? Okay. Full information of this nonlinear conductivity. So there are many words. In general, the answer is no. If you assume the most general nonlinearity depending on U and the gradient U without any restriction. There are counterexamples. I think you can find that in Isakov's book, Inverse Problem for Partial Differential Equations. I believe that's the name of the book. But this technique of linearization approach was as early as in 1990s, developed by Sun and Isakov Sylvester in these two works to, for example, for a simple case, if sigma only depend on the solution U, not the gradient field, not the first derivative. The idea is simple. If you have this assumption, you can notice that any constant lambda is a solution for the conductive equation. Right. Then we can do a sort of a linearization, first order linearization of the boundary DM map by perturb the lambda by small t multiplying by a boundary f. And taking this fresh derivative with respect to lambda. Yeah. So what you get is you can show that you get a directly to normal map associated to a linear conductivity, which is obtained by freezing the nonlinear conductivity at this constant solution lambda. Okay. And then you can immediately use the uniqueness result for the Calderon problem with linear equations to show that if you have identical DM map for the nonlinear conductivities, of course you have identical, by using this linearization, you have identical DM map for the conductivities freezing at lambda, the constant solution. And this gives you sigma 1 lambda equals sigma 2 lambda for all lambda. And that means sigma 1 has to be equal to sigma 2. So that's the proof for this case. And the whole thing is to introduce this linearization approach. That you do this fresh derivative for your DM map. Okay. Then this method was developed to show the inverse problem for other equations like semilinear parabolic equations, semilinear elliptic equations, for some cases for elasticity equation systems, and for hyperbolic inverse problems where you consider wave equations. But all these methods, I guess all these results are using only first order linearization. They didn't look at the next terms in this expansions, what we call expansions of the boundary maps, boundary DM maps. So later this method was picked up by looking at the higher order linearization, which has this recent surge of return of the discussion of this inverse problem for nonlinear equations. So that's the whole story. I guess I'll stop here. And then for the next hour, in half hours, I talk about the modeling of the nonlinear optics and why we consider nonlinear Maxwell's equations, and some results of the inverse problem for Maxwell's equation with Kerr-type nonlinearity and the second harmonic generation nonlinearity. Okay, thank you.
Yeah, thanks, Ting. Any questions? Okay, so we'll reconvene in about half an hour, Ting.
Okay, thank you.
Okay, yeah, thanks.
Later. Bye.